Again, welcome to this Chem Talks in the subject of geochemistry that I have chosen to present to you today. The way that has gotten me into geochemistry is a long one, because I have a lot of age within the subject. But I tend to believe that my lesson from the work that I've done is that I should always be prepared to work on any aspect of ion geochemistry. And many of you may perhaps think that that is extremely narrowing down the subject. In fact, it's not. It is an experience that ion geochemistry is the geochemistry that rule all other geochemistries, almost. And therefore, it is the key into a lot of different problems and processes, and learning the control of the ion in these systems. I work with natural systems, and I tend to summarize the approach that I take by that I like to observe differential and think integral. But in fact, that is not something which is peculiar to I guess my thinking. I do think we more or less work all along that line, so that we make sense in our observations and get the fastest possible correlations in any systems. I work in different subjects, and currently I work in acid mine minerals. I have a project on vapor impact craters and one on Libyan desert glass. I became interested in ion geochemistry in the second year of my agronomy studies at the Agricultural University. I became interested in soil. That was not the purpose that I enrolled at the Agricultural University, but the flexibility of the study program allowed me to pursue the chemistry of iron oxides for the end of my studies. And after having finished my master, I continued with a PhD in pedology on something called plasic horizons in spodosalts. And some of you that recently been to the dentist would recognize the phrase plasic, that is related to the plaque that the dentist work with. So it's sort of a stone horizon that forms within a soil. In this case here, due to contrasting redox zonation in the upper part of the soil. And that kept me fascinated for a long time. I've been affiliated with a number of different universities and surveys, and I've been working in the capacity of a clay mineral, and on relating to the early exploration of Mars that we did at the physics department at DTU. And I'm now currently employed as a lecturer here at the chemistry department. Planetary craters, that is the direct observable result of an impact to the surface of a planetary body. Now they tend and come in many different sizes and many different sub grades. Here is a series from the upper left to the lower right that increase the size of the diameter of the crater, and also the complexities are increasing. We see we come from what we call a simple, regular, bowl-shaped crater to a complex multi-ring crater at the lower right. And in between there is a raised center version of the thing. And all that can be actually quite well understand if we model it as an aqueous solution. I'll return to that in a minute. So that is the physical appearance of a crater event that is going to be like this. What we are experiencing, in fact, is a conversion of this kinetic energy into new textures and compounds. And that is by that we go through a state of extremely high pressure and extremely high temperature and a very high strain rate, higher than anything else we can think of. So there's a relevance to studying these reactions also in terms of preparing new materials. No facility on the experimental surface that on Earth we can have the same conditions. And secondly, we also have the advantage that we are sometimes dealing with events in an order of magnitude on 100-meter to kilometer scale that are unattainable in laboratory setting. And that sort of extends the period during which we can have reactions. As I said before, I'm focusing on what I refer to as late processes. That means they may, of course, have started early, but I think of them as we are able to sample the impact at a very late stage. And that, of course, is very much emphasized that we are actually physically sampling at the current ambient condition of the surface of the Earth. If you want to make a simple comparison, you can take a ball milling experiment. We are all familiar with ball milling, and we do it regularly. But there is actually a version of ball milling which is referred to as high energy ball milling, in which we are able to transform this mechanic energy of the balls into new compounds, and we do that in an experiment. And the same thing is actually going to happen here in meteorite impacts. We are making new materials. The site that I have been picking on is a site known as Hinberry in Central Australia, Northern Territory. Here is encircled, and it is a selected site because although we are very much interested in very, very large meteorite impacts, they are fortunately also very, very old. So when we are searching for fragile materials, we cannot expect them to have survived in the environment for 200 million years. We need to go to younger impact craters, and one example of that is Hinberry. This is a young crater, and is situated also in a continent which is known to have quite low precipitation, which means that the weathering intensity that these materials will be exposed to is rather limited compared to the rainforest of Amazonas. Now, if we take an aerial view on the Hinberry crater itself, we can see that there are a series of depressions here in the landscape. All of these represent a crater. Some of them represent actually two craters, because the craters were so closely spaced that essentially there were no, the material between them were blown away during the crater formation. And again, emphasizing the depression and the rim. The size here means that there are different energy involved. And there's also a characteristic thing that it actually can be difficult to see one of the craters because there's so much vegetation down on it. We see the characteristic subsurface creeks that are marked here by the lines of trees. And if we go close to that, it is very appropriately called the wet crater because it intercepted a subsurface creek. And of course, the water kept flowing into it, and it has, for the lifetime of this crater, been used as a drinking pond for the gears roaming around the countryside. The timeline we can set up, sort of in a condensed version, is that it is approximately 5,000 years old crater. It was witnessed. There is a mouth-by-mouth handed over calling of this place, which indicate that the Aboriginals saw it falling. It became a very crucial crater in the 1930s when when people were working to establish that the meteorite was the cause of the craters. A lot of prior to that, a lot of people thought that any crater would have to be volcanic. And therefore, if we could not find the volcano, there must have been a volcano before. But it actually turned around when we were able to take up a number of the different meteorites. In the case of Hinberry, it's grouped as an iron meteorite, group 3AB, which refer to the nickel content. And ever since that day, you can say the people are focusing on the meteorite. They want to find the meteorite and see it as a very valuable material. To me, it's just a material that gives a lot of energy to a place, and of course a little bit of elements in the case of iron, nickel, and sulfides, cobalt. In the 60s, people turned their interest to impact glasses, and that was spurred by the fact that there was a theory that introduced what we know as glass pieces called tektites, that they actually were made by the moon, from the moon, and from the moon's surface they were thrown out into the space, and eventually they ended up on the surface of Earth. That was partly because they occur at such enormously distance between them, yet they are correlated. So it was thought of, okay, they must come from quite a distance, but they are actually produced on the surface of Earth. Some of them, though, goes traveling beyond the atmosphere of the Earth. It turned out that in Hinberry, only one crater out of the 12, number 7, was the one that had not enough energy to produce glasses. And this sort of simplified the chemistry very much, because there is a variable chemistry of the sediment. It's quartz in some places, it's graywake in some places, but it turned out to be graywake, which we are happy with actually later. So the setting was that we have clarified that the graywake was the origin of the impact glasses, now known as the impactites. In the 80s, people were working a lot on new concepts of cratering, partly supported by new observations. People found craters. I think I mentioned that there is approximately 100 exposed craters at the surface of Earth, and an additional high number in the sediment record. We learned to do lab scale experiments using air guns, which approach the energy regimes of the natural meteorite impacts. And there were much progress in terms of simulation, where treating the sediment as a water body became very popular and effective. I happened to visit the crater back in '93. I was there for approximately 2 hours, and I was the only one of this. We were a scientific trip from Adelaide to Alice Spring, and I was the only one that was lucky to find any piece. And I, of course, grabbed it and took it back home, and it was later our pet to investigate it. This is an example of the meteorite, but not a piece of the meteorite making an impact. This is just the corrosion surface that forms as it flies through the atmosphere. There's a lot of stress on such a piece of iron, and therefore they break up. And in this case, they broke up in 12 major and a number of smaller pieces. And the ones that are affected by the atmosphere, they have this corroded surface. And another group of iron, they are being released as a shock wave is traveling in the meteorite that actually are making craters, and are released in what we call, refer to as shrapnels, referring to the likeness of exploding pieces of ammunition. Now, the impactite, there are 3 types, and type 1 is the most common. The 2 others are rares, but they do exist. And type 1 was the one that I found. Here's a picture of another type 1, actually the one that we call the normal ones, the abundant ones. And we can see that they actually have sort of a surface which embodies the piece of material. I have been fortunately that Ross Taylor shared with me his collection of samples that he collected in '64, before there were too many tourists around the place. And on this cross section here, you can see that there is a number of vesicles of different sizes. in these small pieces, and that is to be emphasized. We're going to look into these vesicles in a moment. Now, the local sediment, the grey wake, just to emphasize to you that we know that we are considerably changing this material. It is a low metamorphic sand-containing sediment. It has chloride, and that is adding some chemistry, because the chloridization of the sediment adds magnesium and aluminum and some hydroxyl and water. And the chemistry of the glasses compared to the sub-grey wake, when we take away the volatiles, are showing a very good correspondence. That means there are virtually no separation of the element during the impact. Evaporation is an actual concern in these high energy processes. So the Hinberry site offered to me a situation where we have been breaking up a major iron meteorite into a variety of sizes. Most of them create small craters. Only one create a crater which have associated with an impact type field. And that is sort of very important, because it simplifies our consideration of what it should be possible to make. Secondly, we have a source of iron, nickel, and cobalt in different possible state, because the meteorite can be solid, it can be melted, it can also evaporate, so that we would have metal gas. Now, a simple time sequence is here to emphasize the knowns and the unknowns of these crater formation processes. In this sequence here, we have a pressure wave, a shock wave traveling from the point of impact, and it's sort of divided in two. The left one is a simple crater. You can see that from the depth and the size of it, and the right one is a complex crater. But the fact that I want to emphasize here is that we have this opening of the depression that is known. We can sort of explain why we have this and observe this bowl, and why we have this rim formation. What this time series indicate initially is that there is also something called the impact plume. It's the brown one in the center, and that has been taken away from the remaining part of the animation. And there's a scientific reason for that. We don't know how it behaves. It's an enormous problem. We sort of initiated and started, and we all agree, or the Koch agree, there must be some material that can evaporate here. But we cannot sort of account for its movement, account for its exchange of energy, and that is an enormous problem. In terms of the pressure and temperature in particular, just to illustrate what peak values we are having, we are getting close to pressures of 300 gigapascals, and we are approaching temperatures of 20,000 Kelvin. And at the same time, we are, of course, also having ambient. Somewhere in the surrounding, we are having ambient, so the gradients are enormous. And we can expect easily to mix up material, end up as neighbors that have been at one extreme and the other extreme. That means deeply transformed and virtually not changed from the initial sediment. But we're going to search for this plume because it's so important. It is the carrier of the distant environmental changes that such an impact will do. And I can only just briefly refer to you that the association of the Chicxulub crater with the disappearance of the dinosaur, with the oncoming of a new geological era, and the worldwide distribution of the originally focused iridium signal, but also other elements can be traced to that, to sediments that are being deposited as a result of the plume. So I think there is good ample scientific reason to go and find this plume. And I will do that just by observing that small piece of the impact site that I just showed you. So to sum up very briefly again, we have this enormous kinetic energy and we bang it into the surface of the gray wake. There are uncertainties. We don't know. We know actually a good deal of the direction, but we don't know the precise direction. We don't know the exact angle, but we make a crater and we can make impact sites, and we've done so in the crater number 7 in Hinberry. So this is the sort of the trophy that I acquired, and you can see just by comparison with what is usually called the normal one, that this one has exposed on it directly all the vesicles, whereas normally the vesicles would not be seen from the outside. So something has modified this material that we had collected here. And we can try to convince ourselves how a normal brittle fracture into this material will look just by making a new fracture and observing it. And we can here on this observation see that there has been a gas melt mixture, and the gas has been able to accommodate itself into spherical shape because the melt would flow around it, and it would be a minimum energy surface situation. And the fracture that we made fresh are extremely sharp. And that we will return to as a significant property of such brittle fractures. So we actually made a new, we investigated the interior and the brittle fractures in this way here. Now the brittle fracture also exposed a lot of vesicles having holes in them. And you see directly into a hole here. And we can magnify that hole into the extent that we can actually see on the surface that this was not a brittle surface break. It was sort of semi-fluid at the state, and when it was released, it was sort of a super stretching process that relaxed back, and we had this drop-like hemispheres before the glass eventually solidified. So there are cooling fractures, and there must have been an enormous differential pressure between these two different vesicles since they forced themselves to open the stuff. And as we look even closer, we can see the details of this cooling morphology. And new material has been displaced, these larvae-looking things, which are also glasses full of cooling cracks. In addition to the, you can say, vesicles with smooth surfaces and holes, there is a bunch of the vesicles that have with them a associated deposit on the surface of the vesicles. Now these details, we can see here that they actually consist of small pieces of the same material as the vesicle surface. So they were sort of physically displaced and dropped to the opposing surface of where the hole was forming. And we can sort of make a simple sketch of that we have in this case here, we just have two different vesicles, one with high pressure, one with low pressure, and then we have a very thin layer of material that breaks down as an effect of the pressure difference, and we displace the material on the opposing side. So we understand locally what this had. Now, macroscopically, this pressure release means that we actually blow off the top of the normal impact side, so that we expose all the vesicles. So this is the reason why that we have exposed vesicles in the impact site that I just mentioned that we found. And that, of course, gives some interesting perspective. Now, are there further pressure release structures that can be related? Yes, there is actually. We are looking down here into a small orifice, which appear to be more sharply defined. And as we are magnifying in the lower panes here, and we shift the focus down into the underlying vesicle, we observe these very fragile looking materials. To account for them, we need to invoke a very fast gas flow from one vesicle to the other, which induces turbulence to the surface. So there will be a local pressure difference, and these local pressure differences can actually pull out the surface. So it's not a laminar flowing gas, it's a highly turbulent, focused but turbulent as it encounters the surface. And that explains this type of, so it's full of gas pressure release structures as it is found. Now, that means that, as I said, the solid surface is blown away. Now, that implies that we have exposed the inside. We're actually looking at the inside, one's inside. And the issue is, when did that happen? Did it happen actually when it was inside the plume? Well, let's see. And we can see by observing the surfaces of these vesicles, the old surface, you can say. And when we compare these surfaces with the ones that we know were brittle, then we can see that a layer of mostly one material have been deposited on top of them. And that layer has a various different orders of cooling cracks. We will see further cooling cracks. And it, very importantly, have also another different material. The whitish looking material is actually iron nickel. That means that there are droplets in that environment that this piece have been flying through, and it has picked them up. But let's go and see further if we can see some cooling structures on and how they were deposited. When we if we take the exposed hemispheres here as the size of the droplets, then it originally consisted of 20 nanometer droplets. And from time to time, there are nice spheres of much larger iron nickel material here, approximately 200 nanometers. And that occurs erratic all over the surface, together with more angular pieces. So we are actually seeing here that it is a later deposition because we are actually deflecting the initial glass droplets deposition when we later deposit the metal. And we can also see here that the sharp rim that used to be here on the brittle fracture, that is covered with new material. This is a much more intensely cracked area. We cannot account for why that is so, but we are very pleased that they are there, because that implies that we have actually been so lucky to sample a material that was solidified as a structure that blow out the surface and continue to travel through the plume, and there it would collect up some plume materials, and we were fortunate to pick it up. And now we have the much sought for plume materials. It's the first crater that we have with this certainty found the plume material locally. So I'm very pleased with that search that we spent some 2 hours to find this unique material. Thank you for your attention.